Our very last topic of Unit 8 and of the semester is the binomial theorem. Yay, we are so close. We almost did it. Hang tight through this video and you will be all set for this semester. Here we are talking about the binomial theorem. The reason it's called the binomial theorem is because it's going to lead us to be able to multiply binomials raised to a power more easily than if we had to actually write those and repeatedly distribute. We'll see what I mean in a second here. Let's talk about what a binomial coefficient is first. That is our first goal. That is what you need to be able to do. One of the things you need to be able to do before you leave this semester is evaluate a binomial coefficient. You also need to be able to expand a binomial raised to a power and then determine a specific term of a binomial expression. Let's take a look how we're going to do it. A binomial coefficient, and we write it this way, n, I usually say n choose r, and it's because it goes back to the idea of a combination, which we don't need to spend time on, but n choose r is equal to n factorial over r factorial times n minus r factorial. We saw the definition of factorial in the last video, so we can use it here. N in this case is 7 and r is 3. So our binomial coefficient here will be 7 factorial over 3 factorial times 7 minus 3 factorial. Let's simplify this a little bit. 7 factorial over 3 factorial. 7 minus 3 is 4 factorial. You can multiply all this out. I want to try to help you simplify this and make this easier to multiply out. 7 factorial means 7 times 6 times 5 times 4 times 3 times 2 times 1 over 3 factorial is 3 times 2 times 1 times 4 times 3 times 2 times 1. Well, the good news about this is that these are all multiplied, right? That means these are common factors. It's like having multiplication times 4 over 4, which is 1. We don't need to write multiplication by 1. Same thing here. All of these can go. And then 3 times 2 is 6, so that can go. So all we have left is 7 times 5 in the numerator and 1 in the denominator. So this is 35. What we will see and what I will start to do as we work through these is noticing that 7 factorial over 4 factorial is just going to leave the product of the numbers bigger than that one in the denominator, right? Because all of these guys will simplify. Let's take a look at the next one. Here, n is 6, r is 0. 6 factorial over 0 factorial times 6 minus 0 factorial. Well, this is 6 factorial over 0 factorial times 6 factorial. We saw in the previous video, I don't think I mentioned it, but it was written off in the side on the notes that 0 factorial is equal to 1. It's defined to be 1. So we just have 6 factorial over 6 factorial. 6 times 5 times 4 times 3 times 2 times 1 over 6 times 5 times 4 times 3 times 2 times 1 is going to be 1. They're equal to each other, right? Numerator and denominator. So that's 1. Here I want to calculate a bunch more of these. I am going to show you how to do this in your calculator, and it's a notation thing, so I need to tell you what another way to write this. N choose r, this binomial coefficient, is the same thing as in your calculator. This is called a combination of n items chosen r at a time. So these two things are equivalent. In your calculator, this combination notation is what is used. Let me show you. We'll do that. What was it? 7 choose 3? Yeah. We enter 7. That's our big top number there. We go into math, over to probability, and number 3 here puts it in that notation. 7C3 gives us that 35 that we calculated. Okay, just so you know, you can do that on your graphing calculator. I haven't looked in Alex to see if the calculator there has this feature. I can look and let you know if you reach out to me. I'll be happy to investigate that. Calculate these. Well, 2 choose 0. Here's a hint. Anything choose 0 is always going to be 1, because no matter what that number is, you're going to end up with n factorial over n factorial, because 0 factorial will always be 1. So this is 1. This is 1. This is 1. We can do this one here. 2 factorial over 1 factorial times 1 factorial is what will be left there. When we do the subtraction, 2 minus 1 is 1 factorial. That's going to be 2. 1 factorial is just 1. 2 factorial over 2 factorial times 2 minus 2 is 0 factorial. That's 1. 3 factorial over 1 factorial times 3 minus 1 factorial. Right, you do 3 minus 1 factorial, gives you 2 factorial. That is 3, because everything simplifies away except the 3. 3 factorial over 2 factorial times 3 minus 2 factorial is 1 factorial. That leaves me 3. Basically saying 3 factorial over 2 factorial there, right? So 6 over 2. Here we get 3 factorial over 3 factorial times 0 factorial is going to give me 1. 4 factorial over 1 factorial times 4 minus 1 factorial is 3 factorial. That's going to give me 4, because the 1 factorial we can kind of ignore, right? It's just 1. Multiplication by 1 doesn't matter. 4 factorial over 3 factorial, remember, this is really what you're doing here, and everything goes away except for that 4. That's what happened up here, and that's what happened up here, right? You just are left with the 2, the 3, the 4. Okay? Notice on these, 2 choose 2, 3 choose 3, 4 choose 4. This is also going to be 1, because these two are going to match, and this will be 0 factorial. These two let's work on a little bit just to make sure. I don't know if I see a pattern in that one yet. 4 factorial over 2 factorial times 2 factorial, right? The first number is the denominator, not denominator. This is not a fraction. The bottom number. The second number is the difference of those two. Well, that is 4 times 3 over 2 times 1. I just took out the 2 and the 1 from one of those. So that's 6. 12 over 2. And this guy, 4 over 3, 4 factorial over 3 factorial times 1 factorial. Guess what? That is the same as this. Just the denominator is switched, and it's addition, it's multiplication, so it gets you the same result. So across the top here we have 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Okay, we could keep going, I suppose. Let's look at this. Let's expand these, x plus y. That means x plus y times x plus y. I really am trying to get to a point here, I promise. X squared plus xy plus xy plus y squared is x squared plus 2xy plus y squared. Okay, let's do this one. X plus y cubed means that result that I just got there times x plus y. We distribute out here. We're going to have 6 terms. X cubed plus x squared y, when I take the x squared to each of these, plus, now let's take the 2xy to each. 2x squared y plus 2xy squared. Now we take the y squared to each. xy squared plus y cubed. Let's combine some like terms here. We have x squared y and 2x squared y would give me 3x squared y. xy squared will combine to give me 3xy squared plus y cubed. Okay, we're going to do one more. We're going to take that result that we just got and multiply it by x plus y. Distribute. X cubed goes to both of these. X to the 4th plus x cubed y. 3x squared y goes to both of them. 3x cubed y plus 3x squared y squared. Now let's take the 3xy squared to each. It'll give me 3x squared y squared plus 3xy cubed plus xy cubed, when I take the y cubed to the x, plus y to the 4th, when I take the y cubed to the y. Combining like terms, I get x to the 4th plus, looks like these two are like terms, so 4x cubed y. Then I have x squared y squared is 6x squared y squared. Here I have xy cubed in these two places, so 4xy cubed plus y to the 4th. Phew! Okay, well, what's the point here? Up here we got x squared plus 2xy plus plus y squared. Here, I'm looking at our coefficients here. 1, 2, 1. 1, 3, 3, 1. 1, 4, 6, 4, 1. Wait a minute. 1, 2, 1. 1, 3, 3, 1. 1, 4, 6, 4, 1. That is interesting. The coefficients here match the binomial coefficients that we found. That is interesting. Do you think we could use those binomial coefficients to expand this instead of doing all this multiplication out, which was pretty yucky, right? We don't like doing that. Wouldn't it be nice if we could write a general formula for x plus y to the n power? Well, we can. We can use those binomial coefficients in this formula. Here's the formula. Let me write it, and then we'll talk through it. We needed that summation notation. That's why we addressed that in the last video. Starting with r equals 0, going up to r equals n, that's how many terms we will have, we are going to do this binomial coefficient, x to the n minus r, y to the r power. Let's talk about what this means. This binomial coefficient gets us the coefficient that we need. The sigma is the adding, right? That's this guy right here, the plus, 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 okay? The x to the n minus r, well, when r is 0, we get x to the n times y to the 0 is just 1. So that's this situation, right? This is if when n is 4. When my n is 4, I get this. N is 4, r is 0. We don't have a y term. Notice that as r increases by 1 up to r equals 1, we now get n minus 1. So the exponent on x decreases by 1, and it increases on the y. And that continues, that pattern continues. The exponents on x decrease, the exponents on y increase. The n, the binomial coefficient here, gives us the number that goes in front. Previously, before having the binomial theorem, to expand x plus y to the 8th, we would have to multiply what we just found, x plus y to the 4th. Really, I guess you could do it by times itself. So you get x plus y to the 4th times x plus y to the 4th. That is x plus y to the 8th. But that gets pretty yucky. You're going to have, like, what are there? 1, 2, 3, 4, 5 terms there. So if you multiply that times itself, you'd have 25 terms. Whoa, we don't want to do that. Before you combined like terms, at least. Okay, let's start with this. In this situation, we are talking about n being 8, right? Let's start with r equaling 0. It is going to be 8, choose 0, x to the 8 minus 0, y to the 0. Plus, that's what the sigma tells us, 8 choose 1, x to the 8 minus 1, y to the 1, because now we're on r equals 1. Plus, now we go to r equals 2. 8 choose 2. The n doesn't change. The n is the exponent that we started with. That's always 8 in this case. X to the 8 minus 2, y to the 2nd. And we keep going. 8 choose 3, x to the 8 minus 3, y to the 3rd. I'm actually going to save us a little bit of time here. You could keep going. The point I was trying to make here is this is a whole lot easier than writing out, multiplying all this business out, but I still want to save us time. We go all the way until r is equal to n, which in this case is 8. So our last one is 8 choose 8, x to the 8 minus 8, y to the 8. Some of these binomial coefficients, it might be helpful to just use our calculator. Let me show you how. We're doing 8 choose 0, 8 choose 1, and so on. We hit the 8, go into math, over to probability, down to the NCR, choose 0, hit enter, we get 1. I'm going to do the same thing, but instead of going through all those steps, I just want to copy that entry such that I can edit it. You do that using this entry button, so second and the enter gives you entry. It copies it over and you can backspace and change that to a 1. And do it again, second entry, backspace, change it to a 2. Second entry, backspace, change that to a 3. Okay. All right, I'm going to use these, and then I'll come back. 1, 8, 28, 56. I'll just try to remember those. This was 1. Here, let me write those down before I forget them. 1, 8, 28, and 56 were the ones we got. This one's going to be 1, by the way. We could go check it, but 8 choose 8 is 1. So we have 1, x to the 8th. Y to the 0 is 1. We don't need it. Plus 8, x to the 7th y. Plus 28, x to the 6th y squared. Plus 56, x to the 5th y cubed, and so on until we get 1 times 1, x to the 0 is 1, plus y to the 8th. Okay, notice the exponents on the x decrease until you get x to the 0. The exponents on the y increase until you get y to the 8th. Okay. This one's a little more complicated because we don't just have x and y here, but the idea is still the same. Just wherever I had an x in my binomial expansion, I now need to put 3x. And wherever I had a y, I'm going to put 1. Actually, let me do something just to make this a little bit easier. Instead of 3x plus 1 cubed, let's do 3n. No, that would confuse us too because we have n's in our formula. Let's do 3, let's use like the Greek letter theta. I know that won't confuse us. Okay, so, oopsie, not squared, cubed. I'm just changing the variable from x to theta. In this case, our n is 3. The x is going to be replaced by 3 theta, and the y is going to be replaced by 1. So multiplying this out, we get 3, choose 0, 3 theta to the 3rd, 1 to the 0, plus 3, choose 1, 3 theta squared. I'm decreasing my exponents on the 3 theta, increasing my exponent on the 1. 3, choose 2, 3 theta, oopsie, to the 1st, times 1 squared, plus 3, wait, hold on, what did I do here? 3, choose 3, let me come down. 3, choose 3, 3 theta to the 0, 1 cubed. So my exponents on the 3 theta, which replace my x, are 3, 2, 1, 0. The exponents on the 1 are 0, 1, 2, 3. And I do always starting with, or always having 3 in that top number, 0, 1, 2, 3. We could go through our calculations and do 3, choose 0. We could also go back up here. I think we calculated those back up here, right? That's the 1, 3, 3, 1. 3, choose 0, 1, 2, and 3. 1, 3, 3, 1. So this is 1. That'll be 27 theta. 1 to the 0 is 1. 3 times, not, oopsie, that's not right. 27 theta cubed. Cube the theta, right? 9 theta squared times 1. I don't need to write. 3 choose 2 is 3 times 3 theta. And then last is 1 times 1 times 1. 27 theta cubed plus 27 theta squared plus 9 theta plus 1. That's what we would get if we multiplied that out. If I had left the x's, these would just be x's, right? It's just a variable. It doesn't matter. I just didn't want to confuse us by writing x equals 3x and replacing that. Sometimes we just want to know the r plus first term of some expansion. So if you want to know the 12th term or the 92nd term or whatever, we can use that. It will be n choose r, a to the n minus r, n minus r, b to the r. Here's the idea. The first term comes when this is 0 and this is n and this is 0. Okay, so these all match, right? But it's the first term when we have zeros in those places for r. So that's why it's the r plus first term. When we're looking for the 8th term of this binomial expansion, we are looking for the situation. We're talking about r plus 1 being 8, right? So that means r is 7. N is 15. The a in the formula is 2x, and the b is 5y. And we just plug that into the formula. 15, choose 7. A is 2x to the 15 minus 7. B is 5y to the 7th. Make sure the r's all match, 7, 7, 7, and they're one less than the term you're looking for. And then just make sure whatever's in this position, that's your A. Whatever's in that position is your B. Let's simplify this a little bit. I'm going to go back to my calculator. You can use that factorial formula if you want. I am going to do second entry again. I'll just have to change the 8 to 15 and the 3 to 7. Just saves me from having to go into that menu again. 6,435. It's a big number. 6,435 times 2x to the 8th times 5y to the 7th. Well, we know when we have 2x to the 8th that we have to raise 2 to the 8th, which is 256 x to the 8th. And here we have to raise 5 to the 7th, which is 78,125 y to the 7th. And now let's multiply all those numbers, right? We can just put all the numbers together. They're multiplied. 6,435 times 256 times that 78,125. Oh my goodness, my calculator overloads on that. Let me see if I can get it on this one without an overload. I didn't expect this number to be quite this big. Let's see if this one will do it. Let's take that number, that's 6,435, times 256 times 78125. Nope, it's given me a exponential, or I'm sorry, a scientific notation as well. This means 1.287 with, it'll be what, 8 zeros after it, moving the decimal place 11 spaces. Probably they're not all zeros. It's probably rounded here because these numbers don't indicate to me that we would get zeros at the end. Not a lot of zeros at least, but we'll just write it like that. 1.287. 1.287 times 10 to the 11th power is what that means. X to the 8th, Y to the 7th. Wowza. Can you imagine if we were trying to do that without the binomial formula? We had to multiply this 2x plus 5y times itself 15 times. That would get a little crazy. So we don't want to do that if we don't have to. Okay? Your problems will not have such crazy numbers in them. I just picked some really bad numbers here. With this 15th power and such, it makes things get a little crazy. That's it. That is the end of the binomial theorem discussion. That is the end of Unit 8. That is the end of the new content we are going to talk about this semester. Make sure to let me know if you have any questions about anything. Enjoy, take a little breather after you watch this last video. You still have some homework to do, but just remember, and of course a final exam to study for, but just remember that that's it for new material. Congratulations, you made it here.